Muy buenos días a todos. Vamos a comenzar. Welcome to all of you. Vamos a empezar esta primera sesión de este día, que es el último, pero no por ello el menos importante, con un tema apasionante, como es el de la Sábana Santa. Vamos a comenzar ya. Vamos a tener varias ponencias, como habéis podido ver en el programa. We want to welcome first of all to Paolo. He's going to talk about the Shroud, and we are expecting this presentation and all the presentations that we are going to have along this session. So welcome to all of you to this first session. We are going to start with Paolo. Paolo is a physicist. He's Chief of Research at ENEA, the Italian National Agency for New Technologies, Energy and Sustainable Economic Development. He's author of more than 340 papers published in international journals, conference proceedings, and chapters of books covering the areas of laser technology, light matter interaction, optics, and beam propagation. He's also member of several international scientific committees. He has been responsible of task groups in European projects. He's also chair of 5 international workshops and 4 international conferences on lasers and their applications. Paolo has been also awarded 8 international patents. Since 2005, he has been involved in scientific studies related to the image of the Shroud of Turin. He has led and coordinated the experiments of laser irradiation in linen clothes, which produces a coloration having chemical and physical characteristics very similar to those of the Shroud image. He was also appointed member of the scientific committee of the Centro Internazionale di Studi sulla Sindone. Sure that it is wrong said, but in Turin, and now he's the deputy director in 2017. So I think that we have in front of us half an hour really, really interesting in this talk that is the title you can see on the screen. Can the body image of the Shroud be reproduced by ultraviolet light pulses? I think that is a really interesting topic. So welcome, and now it's your turn.
Thank you very much, Elisa. And first of all, let me thank the organizing committee for the kind invitation, and also my good friend Cesar Barta, who insisted I come here. And now I can say you were right, Cesar. It was worthy coming here. I am quite excited to present something, not all of course, but something about the Shroud of Turin in front of so qualified audience. The talk develops in 5 points that are listed here, and the first point is an introduction. What is the Shroud and why science is interested in it? The Shroud of Turin is a very large cloth. It's 4.4 meter wide, long. That is more or less like this table, and is 1.1 meter wide. And people is interested in the Shroud mainly because it contains 2 images of front and back, images of a man, bearded man, who has been crucified and tortured exactly according to the Gospel. And Saint John Paul II defined the Shroud as the Gospel mirror. And the Pope Pio XI said the Shroud is the 5th Gospel. So let us see, let us analyze this image. But here it comes a surprise. Can you see any image here? I cannot. This is a photograph without contrast enhancement, in natural light of the shroud as it really appears. And you cannot recognize a figure, let alone two figures. So to see the shroud, you need to make a photograph and increase the contrast. Why this happens? Because we will see in the next slides that the image is a sort of accelerated aging of the cloth, of the linen, of the cellulose that makes the linen. But of course, all the other part, which are not the image part of the shroud, of course is aged, because it has, say, several hundred years, to say the least, probably 2,000 years. So it's a common experience to see a cloth of linen, maybe of our grandfather, our grandmother, that after 100 years becomes a little bit yellow. Yeah, this is oxidized, exactly like the Shroud of Turin. So this makes the image low contrast image, so our eye cannot recognize it very easily. So let us see what happens when we increase the contrast. Well, when you increase the contrast, you see much better the face, hair, bird, a body. On the left there is the frontal image, on the right there is the back image, and inside the shroud, together with the image, there are also several marks. So there are water stains that have been used to probably to switch off the fire the shroud suffered of a fire in 1532 when it was in Chambéry. And in fact, there are several bar holes, just because it was closed in a box. The box was decorated with probably with some silver metal, silver founded, and then the drops of silver fell down the shroud, making all the holes you can see here. And there are, of course, several blood stains on the chest, on the nail, and finally there are scourging bruises all over the body, but especially on the back. So the most comprehensive analysis on the shroud was made in 1978 by a group of scientists, mainly American scientists, under the aegide of STURP, Shroud of Turin Research Project. And they had 5 days and 5 nights working 24 hours a day to analyze the shroud with the best tools, the best analytic tools available at that time. And here I can try to make a very short summary of the results that are written in about 30 papers published in international journals, highly respected international journals. So what the STURP found that the shroud image is not a paint, is not a scorch. It has no directionality. I mean, there are no shadows on the image. And however, the image has some fading. And the fading is not due to a different color. All the colored fibers of the image have the same RGB value, that is, has the same color. So what is the fade due to? It's due to the fact that it depends on how many colored fibers are close each other. If they are very many fibers colored next to each other, to our eye it appears darker yellow. When the colored fiber are next to not colored fiber, it appears to us as a less intense yellow, a more dying yellow. So this is known as the half-tone effect. And this shading contains three-dimensional information, possibly related to the cloth-to-body distance. The image is very superficial. The color depth is less than the wavelength in the visible range, less than 0.6 micrometer. But recent analysis, I will show some result, has shown to be 0.2 micrometer. Can you imagine how much thin is a 0.2 micrometer? You can try. Just take 1 millimeter, okay? It's something like this, 1 millimeter. And then this millimeter, you have to divide it in 1,000 parts. And then you take one of these parts and divide it further 5 times. Then this is 0.2 micrometer. It's so thin that it's even difficult for us to imagine. So if it is not a paint, what caused the image? What made the image? Is due to an unknown process that caused oxidation and dehydration of the glucose molecules which make the cellulose of the linen. To some extent, the color is a result of an accelerated aging process. An interesting point is that when you illuminate the shroud with ultraviolet light, that is not with the normal lamp light, with the ultraviolet light, they appear some halo around some of the blood stain. And also, the Sturp determined that under the blood, there isn't color. So the fibers, the threads are not colored when they are behind the blood stains. So this is possibly due to the fact that the blood went before the image process, the unknown image process. And finally, blood stains contain hemoglobin and serum albumin. So in 1980, during a press conference, the Sturp responsible made these final remarks. We can conclude for now that the shroud image is that of the real human form of the scourged, crucified man. Is not the product of an artist. And you can understand why it's not the product of an artist. Because the characteristics that I mentioned before of the image are absolutely unique. You cannot think to make a paint which is 0.2 micrometer thick. It's impossible, impossible. You cannot imagine that an artist make one colored fiber 20 micrometer wide next to not colored. It doesn't exist such ability. You should work with a magnifying glass for each fiber. And in one thread, there are 250 fibers. It's impossible. And then Sturp continue. Blood stains are composed of hemoglobin and give a positive test for serum albumin. The image is an ongoing mystery. And until further chemical studies are made, perhaps by this group of scientists or perhaps by some other scientists in the future, the problem remains unsolved. So this is the main point. After 30 papers, after hundreds of measurements, Sturp was not able to say how the image was formed. So here I summarize in this table the main reproduction attempts. As you see, they started in 1902, more than 1 century ago, with Vignon, which used the vaporographic technique. On the column on the right, there is the main problem, which makes the difference between the result and the image on the shroud. And as you see, none of these attempts was able to reproduce 100% of the characteristics of the shroud according to the measurement of the STURP. It's also interesting to note that before the STURP, before 1978, one attempt to reproduce the image of the shroud was considered successful if, at a naked eye, it looks more or less like the shroud. And frankly, it is not so difficult. You can do it. But the STURP results pointed out that there is a microscopic complexity in the fibers of the shroud. And it is this complexity that up to now nobody was able to reproduce in full. And among all these attempts, probably the most close to the shroud image was the last one made by my group at the ENEA Research Center of Frascati using ultraviolet light. So let us see why we use ultraviolet light. Here is written a sentence which you can find in every textbook university because it's a general property of ultraviolet light in every light matter interaction. So ultraviolet interact with the matter by a photochemical reaction without heating the material. And also ultraviolet makes some change just on the surface of the target because it cannot penetrate deep. And the shorter the wavelength of the ultraviolet, the thinner will be the effect on the target. And this is valid also in air. The shorter the wavelength, the more the absorption of the air, and the less light can travel. So these are general properties of UV light, but when applied to the shroud, they become very interesting because the ultraviolet radiation is an acting at distance energy which could be able, in principle, to obtain 4 of the main characteristics of the shroud. A thin coloration depth, because it cannot penetrate deeply in the material, including linen. A contactless action. Why? Because it's important. Because when you see the shroud image, you cannot, you can be sure that that image was not obtained by the cloth put very close to the body, because otherwise you will see a very large image, the so-called Agamemnon effect, the mask of Agamemnon, which is very large, of course. You can also make experiments at home. If you paint your face and take a towel, white towel, and put your towel just around your face and they see what happens, you will see your face, which is very wide, because this surface is a 3D, is transformed in 2D surface and becomes very large. On the shroud, we cannot see this. This means there is no contact of the cloth to the face and to the body. So you need something which acts at a distance. And then UV is a low temperature coloration process and has a coloration that the fading that depends on the cloth to body distance. This is a photograph of our setup. We use 2 different lasers with much different characteristics. In common, they that emit ultraviolet light pulsed. The duration can change between, say, 20 or 30 nanoseconds, billionth of seconds, up to 100, 120 billionth of seconds. This is a photograph of the oscilloscope. In this case, you see there is a pulse duration of, let me say, about 12 nanoseconds, so 12 billionth of second. And here is a photograph of a piece of linen irradiated by the ultraviolet light. Pay attention, you see a bluish light. Bluish light is not ultraviolet. Ultraviolet is invisible to our eye. We cannot see ultraviolet. But we can see the blue fluorescence of the linen, and so the blue fluorescence of the linen tell us where the laser arrived, where the laser impinged. And on the left here, you see a photograph of linen colored by ultraviolet light. It's difficult to see. It has a low contrast, exactly like the Shroud of Turin. The image of the Shroud of Turin you have seen before has a low contrast. But exactly like the Shroud of Turin, when we illuminate the same piece of linen with ultraviolet light, you see that there is a dark stain in the middle here. This dark stain. This dark part is the irradiated linen, the yellow linen, which give a lower fluorescence than the not irradiated part. And this is exactly what happens for the Shroud of Turin. When we illuminate with UV the Shroud of Turin, the image appears darker, much darker than the surrounding piece of linen. Here is a photograph of a piece of one thread. You can see it is, I don't know if you can appreciate, there is yellow here and here. In the middle is not yellow because there was another thread on. And so ultraviolet didn't penetrate the thread, so didn't arrive in the central region of this piece of thread. And here you can appreciate what I told before, that is a thread is made by about 150 to 250 small cylindrical fibers. You can see here a larger view. You see these small cylinders. Each of these small cylinders is a fiber. 200, say around 200 of this fiber make one thread. And each fiber is say, wrapped by a very thin, say, surface that is called the primary cell wall. And the primary cell wall is 200 nanometer thick, is 0.2 micrometer thick, exactly like the penetration depth of the color on the shroud. That means that the color of the shroud penetrates only the primary cell wall, which is around each fibril. And just to give an idea, each fibril here is 20 micrometers wide. And here is an example of the depth of coloration with ultraviolet light of a thread. This is a cross-section of irradiated linen threads. You see on the down is the irradiated linen thread with the 308 nanometer, which is near ultraviolet. On the left, you see another thread irradiated with the shorter wavelength. And you can see that penetration depth in the case of the shorter wavelength is much less. So we have to use wavelengths as short as possible. That is, a hard ultraviolet as possible. During these experiments that lasted a couple of years, accidentally some fibers were damaged, just mechanically damaged. Sometimes you have to take it off a single fiber. It's not easy. And sometimes you damage the fiber. And in this case, was very important, this damage. Why? Because in this way we had a good view of the fact that inside the fiber there is no color. You see, the central part is not colored. The outside part is colored. And then I can show you, here are 3 shreds of the primary cell wall that came out. The one in the middle is at focus. The other 2 are out of focus. But let's concentrate on the middle one. These are shreds of the primary cell wall colored, and inside no color. That is quite a good evidence that in this case we were able to color only 0.2 micrometer thick penetration depth of the ultraviolet light. So we were able to obtain what it seems impossible to obtain, that is a coloration depth so thin. And then let me get back to the half-tone effect, because I guess that none of us has a confidence with this concept. The half-tone is a technique which is used till now for having a gray level of a photograph, for example, using only 2 colors, white and black. So just to spare about the color, is costless using only white and black. I can obtain all the shade of gray. How it's possible? In this way. Just putting dots that change in size and in distance that generate a gradient-like effect. So to make an example, this figure you see on the left is seen at the microscope. When I see at a distance the same image, I obtain this result. You see, I have a gradient of all the gray shadow, the shading. The shroud works in the same way. There are small fibers colored next to uncolored. And for example, if I have 1 colored, 2 not colored, and then again 1 colored, in my eye, integrate everything, and it appears a dime yellow, not very strong yellow. But if I have all fibers next to each other are all colored, to me it appears a darker yellow. But really, the yellow is always the same. Like in this case, the black is always the same. It's just the distance between black that make the difference. And just by chance, during our irradiation, we obtained this half-tone effect. You can see here a microscope view of the thread of the linen. Some of them are colored next to not colored fibers. You can distinguish the fibers are these small cylinders. And so, to some extent, we obtained a glossy shadow-like, fading-like in the Shroud of Turin. And by the way, this was just by chance. Why? Because of an imperfection of the laser beam. So, perfection that doesn't drive us to very good results. It's imperfection that is more useful sometimes. You see here the spatial profile of the laser is brittle. There are many peaks and down, peaks and down, peaks and down. And when it happens, then on the peak you are above threshold for coloring, and next peak down you are below threshold for coloring. You have 1 colored fiber and 1 not colored fiber. But this was obtained really by chance. So I have shown you all the results we obtained till 2015. And to some extent, they are all the results. And we showed that ultraviolet irradiation produces a coloration that match several characteristics of the shroud. Superficiality, half tone, color that can be finely tuned to the correct value as in the shroud, reduced fluorescence when illuminated by ultraviolet light. All these are physical characteristics, but what about chemistry? It's not sufficient to have a similar coloration from a physical point of view if the bonds, chemical bonds, are totally different. In this case, you will have anyway a different coloration. You have to join both the chemical and physical properties. So the question is, what are the chemical bonds generated by ultraviolet light in the cellulose of flax fibers? And then very recently, actually last year, we faced this problem and used a state-of-the-art Raman spectrometer equipped with the confocal microscope. This is really a top product of Oriba, quite expensive really. And so let me explain first what is the Raman effect. If I send a laser beam, for example, a green laser beam, on an object, every object, the object reacts, giving me back another light. But this light has not the same color of the laser, has a different color. Sometimes the difference is very little. And when it happens, it is in an effect of the so-called Raman, which was a very famous physicist, Indian physicist, that more than, let's say, 150 years ago, even more maybe, found this effect, not using laser, of course, but he found that the spectrum of the reflected light depends on the vibrational state of the molecules of the object. To some extent, is a fingerprint of that molecule. What I mean is that if I have a database with all the shift of all the molecules, when comparing the data sheet with my results, I can recognize, there is this molecule. So it's a fingerprint. And now, of course, today, the Raman technology is very powerful. One of the most powerful tools we have to recognize the chemical bond of practically every object. So comparing the Raman spectrum of flux before and after the ultraviolet irradiation, we can know how changed the chemical bonds. And this is very useful if we want to understand what happened to the chemistry of the ultraviolet irradiated flux. A nice property of Raman is that it does not require removal nor destruction of the sample. So you can repeat the measurement all the time you like, because the sample is not changed by the stimulation of the laser, provided it has the good characteristics, of course. Well, this is a result. This is a graph of the intensity of the reflected light as a function of the wavelength or of the energy. Don't tell me why, but spectroscopy like to use a unit of measurement. This is called the centimeter minus one. I don't know why. Really, for me, it's also difficult because I am in the habit to reason in terms of wavelength. I'm a physicist. I reason in terms of wavelength. And in this case, I have to make a calculation. But anyway, here we are in the infrared region. And you see, there are 3 different plots. The blue one is a not irradiated linen. So I measure the Raman shift for the not irradiated linen. The red one is the linen after irradiation with extreme ultraviolet light. That is a very, very short wavelength, around the 30-40 nanometer wavelength. And finally, what interests to us more is the green part, because the green part is the Raman spectrum after ultraviolet irradiation. And you see here there are several differences. One of the biggest difference is the change in this peak. You see, this is not irradiated, and this is the ultraviolet irradiated. So there is a drop, really much smaller. And what is this bond? The COC, carbon oxygen carbon. The carbon oxygen carbon is the bond which put together the glucose molecules in the cellulose. Cellulose is made by, say, 3,000, more or less, 3,000, 4,000 glucose molecules joined together by a COC bond. And so, if I see that the number of bonds goes down, that means ultraviolet has broken these bonds. And then it has created some smaller chain, no more 3,000, 4,000, maybe 500, 400 molecules of glucose put together. So I am changing something. But this effect is mainly an aging effect, because the aged cellulose of linen becomes broken. So the chain are shorter, so it is due maybe to friction, to light, to temperature. There are different mechanisms that just shorten the group of glucose chain. So I am doing something about the aging with ultraviolet. And then I see that there are some new bonds, carbon-carbon, that go up with respect to the not irradiated, and CO that goes up with respect to the not irradiated linen. And in this table, don't worry if you don't understand everything, but it's just to give you some numbers. RH, the first one, the RH is the degree of polymerization, which is a difficult word to say what I told you before. The higher the RH parameter, the longer are the chain of glucose. And you see that there is a drop of 64% down, less than the not irradiated flux after UV irradiation. This means what I told before. We are breaking several of these bonds. We are making the linen aged. And then there are other parameters. I'm not here to, I have here, because it's difficult even for me to remember exactly what they are meaning. But in a few words, O is a parameter which gives you information about the oxidation in general of the cellulose. That is how many oxygen molecules are inside the cellulose. And you see that after irradiation, there is a double, more 160%, 116% of this oxygen. That is, when I break this molecule, oxygen attach, and the wool cellulose becomes more oxidized. And the last two, MCC and MCO, they are parameter proportional to the number of new bonds, double bond, CC, carbon-carbon, and double bonds, carbon-oxygen. And you see there is quite a strong increment, especially of the carbon-carbon new bonds. And we will see why this is important. Okay. I have to run because eventually I was too slow before. So what happened? The photooxidation of cellulose, that is the breaking of polymer chain, the drastic increase of double bonds CC and CO, and there is a point, is that double CC and double CO taken alone cannot give you a yellow color. They are not able to change the color. But when you put it together in a so-called conjugated chain, that is double single, double single, double single, you create what is a conjugated carbon-oxygen bonds, which absorb the green-blue part of the visible light and emit yellow light. So the fact that we found that bonds highly increasing after UV radiation means that we are close to what Adler and Heller found on the Shroud of Turin, yellowing due to chemical bonds conjugated. And then there are the conclusion. Very fast. Of course, these are. Sorry, I have to run and just stop in the most important point. I didn't mention that the ultraviolet coloration is a threshold effect. So below a given intensity, you obtain zero. You obtain no coloration. Above a given intensity, you have a coloration, but you, if increase too much, you burn the cloth. So you have to find the optimum value to find the good range of linen coloration by ultraviolet. There is a photochemical coloration process, of course. The hue of color depends on the wavelength, but the most important point is that I can change very finely the color just acting on the number of shots laser. We observed a few irradiated fibers whose coloration was just on the primary cell wall, leaving the medulla, the inside of the cellulose, not colored. I didn't have time to show you the latent coloration, but it is important, it is interesting. Sometimes you obtain a latent coloration. What's the meaning? After irradiation, I see nothing. But when I hit with the iron, simple iron, I hit the region where I have irradiated the cloth, it appears the coloration. What I did using the iron, just accelerated aging. And in fact, we tried to color below threshold, that is latent coloration, no coloration appears at the naked eye, put it in dark for 2 years. After 2 years, we take off the linen and it appears coloration. So this is natural aging. Why people are interested, because, especially historians, because historians are interested in the possibility that the image on the Shroud of Turin didn't appear immediately. Because on the Gospels, nobody speaks about this image. But it appears later. Maybe 2 years later, 3 years later, we don't know. This is just a possibility. But the latent image is interesting characteristics. Again, the reduced fluorescence, the half-tone effect we mentioned. The Raman spectra is the newest result I have shown today, and show that the photolysis, that is the rupture, the breaking, generated a radical that promoted the oxidation and dehydration of the cellulose, with the formation of a large number of carbon-oxygen double bond and carbon-carbon double bond. When they are joined together, they are conjugated, they absorb the violet blue light of the visible spectrum and giving a flux a yellowish hue. So, in practice, we obtained with ultraviolet light a linear coloration which have the great majority of the physical and chemical characteristics of the shroud, which is called the impossible image. But when considering the highly not conventional hypothesis of John Jackson about a radiating body, the UV light is compatible with this hypothesis because it travels in air not very much after long distance, well after a short distance, so it is compatible with this hypothesis. However, when obtaining a shroud-like coloration by ultraviolet radiation, it does not mean that the body image was really obtained by a flash ultraviolet light. From a scientific point of view, we can say it's not impossible that ultraviolet light played a role in the formation of the image. Never ask science to explain what is outside science. A radiated body is outside. That's outside science. And the last two slides. Philip Bull in the Nature Online in January 2005 wrote this sentence that I like very much because it's true. The scientific study of the Turin Shroud is like a microcosm of the scientific search for God. Does more inflame debate than settle it? Yes, unfortunately, is in this way. And yet, the Shroud is a remarkable artifact, one of the few religious relics to have a justifiable mythical status. It is simply not known how the ghostly image of a serene bearded man was made. So finally, what is the Shroud? Our good friend, late Barry Schwartz, unfortunately passed away a few months ago. He wrote several times, we could tell you what is not the Shroud. Not a painting, not a photograph, not a scorch, not a rubbing, but we know of no mechanism to this day, he mentioned natural mechanism of this day, that can make an image with the same chemical physical properties of the image of the Shroud. So people often ask me, does this prove the resurrection? The answer to fate is not going to be on that piece of cloth, but more likely in the eyes and ears of those who look upon it. And I agree more than 100% with this sentence. Thank you very much for your attention.
Thank you.
Sorry.
No, you're welcome.
5 minutes more, sorry.
We are really happy listening to you. We will like to have more time to keep on listening, but we are really in a hurry, but I think that we have time for at least one very short question, okay? We can do it.
Yeah, if I understood. When you break the chain, you act just on the fragility of the cloth, of the cellulose, and then of the fibers, and then of the threads. You don't act in any other way. It's just an accelerated aging. I put it in evidence just because the Sturp defined the image on the Shroud as an accelerated aging of the cloth. So when you break the cellulose chain, you are just aging the cloth. It has no effect on the color, no effect on anything else. Just it becomes more fragile. It was this the question? Okay. No, I don't think. No, the action is on the fur in less than 1 micrometer thick. Below it there is no problem at all, of course. But in fact, the Sturp scientist when they made some, they taken off by using a tape some fibers of the image, they realized that the fibers of the image that remained on the tape were really more fragile than the other part. Why? Because they used the same tape on a not image region, and they found difficulty to find fibers. When you do this work on the image, there are much more fibers. So that means they are more fragile. Only on the surface.
Okay, thank you. I think that we have not more time, so thank you again for your really, really nice and interesting presentation. Thank you, Paolo.